That's it? That's it? We're just live?
Yeah.
Okay.
No there, just live.
You asked to go
I
live.
did. It's possible that in the last few weeks, there's been some shenanigans involved, and now you just like we're live. It's as if this process gets smoother over time.
As a veteran of the last 4 weeks, I can vouch we haven't had a problem in 4 weeks.
This is it's like
Nice.
downright seamless. So now's the point of the show where I whine about my weather. And so now we're expected to get cold temperatures here, going down to minus 15 Celsius. And
Ooh.
I know, Nick, that's like what you're doing every day, but that is not.
Speaking from the subarctic.
Yeah, that is not right. That for Vancouver Island, didn't I last week say that we're the Florida of Canada? I literally have to eat my words now because we are about to experience a cold snap of just historic proportions, like 5 degrees colder than the record coldest temperature.
Fraser, we hit minus 32 with wind chill a few days ago.
Oh, yeah.
And I came up here from Phoenix, Arizona.
But you chose to go there.
You chose to live in Vancouver.
I sure, because of its mild coastal climate, as evidenced by the last. But I mean, we had 40 Celsius in the summer, which again was 10 degrees warmer than we normally get. And this is all in Celsius.
I'm going to one up you once again. This past summer we had 43.
Normally, coming up to the West Coast, the weather's fine, but it's not.
Fraser, it's all my fault. It's all my fault, and all the clouds are all my fault.
Oh, really? Did you buy a telescope?
I bought a new telescope.
Oh, what did you get?
Ooh.
That's what
EV scope 2.
You got an EV
The
scope?
Unistellar EV scope 2.
Oh, how do you like it?
Yeah. I'd love to be able to get out there and collimate it and everything, except we've been having high winds and really cold weather.
Yeah,
so,
and you destroyed the weather for the entire planet. So how could
you leave all the way to England? So yeah.
It got cold here too, 41 degrees Fahrenheit. Yeah.
Yeah, that's absolutely Carolyn's fault.
Oh, that's frigid.
Yeah.
For Southern California, and I'm from Ohio, so okay.
Yeah.
Fair enough.
Get out your down-filled coat.
Yeah. Although it is funny how you adapt, I think, to the weather.
Yeah.
I know even my wife is becoming more and more accustomed to cooler. Apparently she hasn't. So I take it all back. Apparently.
I actually got made fun of today for saying I was kind of enjoying it being cold for a change. The people here in Lethbridge pretty much said, "What are you, nuts?"
Yeah, Lethbridge is that's cold. Man.
Oh yeah.
Yeah. All right. Well, we are nearing the 5-minute mark, so I think I'm going to start this show. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, December 22nd, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about James Webb and what it's going to be looking at. New information on the clouds of Venus. It is apparently cold in space. Pam will tell us more. Hayabusa samples and crazy geology coming from Pluto. Joining me this week, we've got on my screen, Carolyn Collins-Peterson. Carolyn.
Hey there, how you doing?
Good. And you were just telling us before the show that if anyone's having bad weather, it is your fault.
Pretty much. New optics have landed at my house.
Congratulations on getting a new telescope. I wonder what's going to happen when James Webb launches, because won't that just, like the most powerful telescope that's ever been built, won't that just knock out terrestrial telescopes for a decade?
Yeah, the entire planet's going to be enshrouded in clouds. This is my prediction.
This is why we're sending it to L2.
Well, yeah, I know it's not going to carry. It'll be fine, but it's just going to create a place of such obscurity that no one else is going to be able to observe. That's the follow-on. And I say that I'm not superstitious at all. Anyway, we got Pam Hoffman. Hey, Pam.
Hey, Fraser, how you doing?
Good. Have you had a chance to see the comet yet?
Well, of course we got clouds and rain. As soon as it was in the evening sky, when I generally like to go out and look, couldn't really do it.
Oh,
Yay, team!
go team! Yeah. Well, hopefully it. I've seen a lot of pictures, so I think this is our chance of. I mean, it's not the great visible comet that we deserve, but it's one to at least look at to remind ourselves that comets exist. So it'll have to do. And we got Dr. Nick Castle. Nick, welcome back. This is
Thanks. Good to be
fourth time
here.
in a row.
Yep.
Right on.
Tic-tac-toe.
Awesome. Well,
Connect
good.
4,
You're
one of those
then,
things.
yeah. Well, then I expect nothing but just the highest quality science communication today from such a seasoned veteran.
Are you kidding me? I'm totally burnt out after 4 weeks of this.
Understood. All right. Before we get into our special guest, I just want to give a huge thank you, shout out to our good friends of the Weekly Space Hangout crew. They are our fans, our executive producers, and a wonderful community. So if you want to find a bunch of like-minded space friends, then you should go to the Weekly Space Hangout crew website, and then that will connect you to all kinds of wonderful resources. Go to wshcrew.space. Hey, it's right there on the screen, and you can find out more. All right, let's get into this week's special guest. We've got Dr. Jake Abbott. Jake, welcome to the Weekly Space Hangout.
Thanks for the invitation.
The question I always ask is, who are you? What do you do?
I'm a professor in the Department of Mechanical Engineering and the Robotics Center at the University of Utah in Salt Lake City, Utah.
And you came across our radar because of a paper that you worked on with a bunch of other people that just came out in Nature a couple of months ago about manipulating objects in space not touching. Can you explain this?
Yeah, so we've been working on the area of magnetic manipulation of objects without contact for over a decade, but those objects have always been ferromagnetic in one way or another, either permanent magnets or some sort of ferrous metal. And I started getting interested in the idea of using eddy current induction-based methods to manipulate metals that aren't magnetic, so metals like aluminum and titanium. And around the same time I was getting into the idea that that could be done, I became aware of this problem of space debris and that it's almost all made of aluminum. And sort of the two ideas came together at the same time. It wasn't like one led into the other. It was sort of, they both kind of came to my knowledge at the same time. And so we've been trying to tackle that problem.
So what are eddy currents?
Yeah, so basically, anytime you have a conductive material, that usually means a metal, and you expose it to a magnetic field that's changing in time, then the electrons move within the material. And you can almost imagine it like swirling, and those electrons moving effectively behave like a little mini electromagnet in that instant that the magnetic field is changing in time. And then that little electromagnet that lives inside the metal reacts against the very magnetic field that made it, and that generates forces and torques. And if you understand them well enough, you can use them and sort of solve the inverse problem, and then you can do manipulation with that set of physics.
What kinds of applications does this sort of technology have, even just here on Earth?
It's unclear to me if it does have applications here on Earth. I mean, the forces and torques are quite weak relative to the types of magnetism that I'm used to dealing with. And so they're small compared to the weight of the object. So, like, for example, levitating an object against its own weight would be very difficult. Now, you're actually showing a video right now of us manipulating an object that's floating on water, a copper sphere. So, you know, the forces and torques are sufficient to move things on Earth, but I think really the killer app of this is manipulate things in space, especially things where you maybe have more time than humans are used to doing manipulation tasks.
Right. And so what kinds of metals? You mentioned aluminum. This experiment is showing copper. Are there any limits? And then can you even do non-metals, or does it have to be metals?
It needs to be conductive. So I would say, you know, any metal you can imagine. And also the assumption here is that this metal is non-magnetic. If this were a ferrous metal or a nickel, it would respond to the magnetic field in a much stronger way. And we already understand that. And so we're assuming you're not considering those metals, but really any other metal would work. And yes, if you make another material conductive, possibly by embedding metallic particles in some sort of polymer matrix, if you make another material conductive, it also could be manipulated.
That's interesting. And then, as you, I guess, identified, so let's talk about the space application that you were talking about. So what are you and your team envisioning?
So One of the main problems if you're trying to deal with space debris, and space debris takes a lot of different forms. It could be a satellite that once worked, doesn't work anymore, and you want to repair it potentially, or you want to deorbit it, meaning basically slow it down so it'll burn up, right? Or you want to capture it with some sort of more traditional robotic manipulator. A lot of these objects in space are tumbling, and they might already be damaged potentially. So they're fragile, you should imagine. And if you were to try and reach out and grab these objects with a traditional robot, you could just create more space debris, either by breaking up the object or by breaking the robot arm itself.
Yeah, absolutely.
And so really the main application for this is to detumble an object in a controlled way such that some secondary process can happen to it. Either you deorbit it, or you grab it, or repair it.
What's the range? Like, how far could you affect a target particle?
So it's a complicated question. The forces and torques basically fall off with distance to the 6th power.
Ooh.
So it's bad, right? It's
Inverse
a bad scaling.
Sextuple law.
Yeah, you want to be as close as you can to these objects, but the fact of the matter is, because of the physics of generating the forces and torques basically scales linearly with a lot of the inputs, all that will happen if you get farther away, or if you have a weaker magnet, is it just takes longer to detumble something. There's not a kind of a critical point at which you can't do it anymore.
Right. I mean, so I'm imagining like you have some spinning dead satellite with solar panels and boom arms and communications booms that are sticking out of it. You would want to have and what would a manipulator look like? And I'm just sort of imagining the operation to try to actually perform this operation. Like, unless you're still gonna have to get, are you gonna have to get in a couple of meters of it at its most dangerous point, or
I think that's
tens of meters?
I think that's the right way to think about it. I mean, you imagine this object as it's spinning. You can imagine that it traces out a minimum bounding sphere. So there exists a sphere that the whole thing always stays inside as it's spinning.
Yep.
And then you probably just add a small factor of safety, and you want to get as close to that sphere as you can. And so, but it could very well be that if the object isn't perfectly spherical, and depending on the axis that it's rotating on, you may actually be able to get much closer than that sphere if these boom arms or antenna or whatever you're describing are sort of on the orthogonal to the direction you would kind of come in, And in terms of what you'd want to imagine for the manipulator, so if you look in this image here, if you look at our experimental setup, you see these sort of copper cubes that are labeled omnimagnets. And those are basically a point dipole magnetic field source. Each of those cubes is really 3 magnets, mutually orthogonal to each other. And your end effector of your robot that would do this would be something like one of those, likely.
Right.
Yep.
Right, I see. So I can kind of imagine like you would come close to your tumbling satellite, observe it for a while, track exactly to the millimeter almost where that boom arm is swinging past, and then put one of these manipulators right at that point, and then each time it swings by, it receives a tiny little torque. Maybe it takes you a month, but you slow it down. I mean, is that the kind of time frame you'd be looking at, like days, weeks, months, maybe, to get it into a safe attitude compared to the capture vehicle?
Yeah, I think the timescales really could vary quite wildly based on your specific circumstances. And we're just sort of starting now to look at specific cases where we can put some real numbers on sort of real objects. But, our study was very much a first study. I mean, no one had ever shown manipulating an object dexterously like this that's not magnetic. So the objects we've manipulated so far and really understand well are solid spheres. That's sort of the basic object all other objects deviate from, you know?
Yeah.
And
yeah.
so that's the only object that we really understand really well at this point.
One of the really interesting ideas that's been proposed for cleaning up space junk is something that is more like at a distance, but dealing with the ferromagnetic and essentially attempting to put out an electric field that will summon a piece of space junk slowly towards the spacecraft and act like a bit of a tractor beam, and the spacecraft could then go and gather, even park them or deal with them. But it was always considered to be at arm's length. And so this idea, do you see these kinds of technologies coming together? Like you could sort of do both at the same time with one power system, but I guess different electronics?
Yeah, I really don't know much about that idea. I will say...
Paper.
Yeah, I would like to see it.
Yeah.
I will say that this phenomenon that we're using cannot be used to attract something. It's sort of no matter what combinations of forces and torques you generate by a given motion, there's always a component of the force that's pushing it away from you. And so
right.
We actually imagine this happening in kind of a caged way. So rather than approaching this piece of debris with one of these magnetic sources on an arm, you'd probably approach it with at least two, and they'd sort of straddle either side of this object. And they'd be working in concert with each other to detumble this object and keep it centered between them. So each of them is pushing, but it's just really maintaining it in a common center.
Yeah, I was thinking even like a lasso or a net arrangement that would kind of encapsulate it and you could move it around that way.
Certainly, I think once it's not spinning anymore, then a whole world of options opens up of how you might grab it and pull it towards you. And we are actually right now looking at almost creating something like a vacuum cleaner. So if we had multiple of these sources and they were spinning in a coordinated way, if there were many little pieces, there would be sort of an area in which the little pieces would sort of collectively be gathered together and come in. So rather than you trying to target each one individually, you can sort of imagine sort of an area or basin of attraction of lots of little things. And then maybe like a vacuum cleaner, maybe you have those things get gathered in some sort of net or bag or something. You know.
The other kind of application that I'm sort of thinking about is the, say, construction of on orbit equipment. Like probably future generation space telescopes are going to be assembled in orbit, probably autonomously. And so I can kind of imagine something like this being able to, I mean, obviously you could use a Canadarm. Why wouldn't you? But I imagine for really fine motor control, things like that, like if you really need to precisely connect things together, then that might be another way to go as well. I can just imagine that like one of these being attached to a robotic arm anyway.
I think that's a very interesting idea, and one potential benefit of why you might think about doing that is any traditional robot you use, there's going to be pressure points, right? That eventually you're going to have some sort of hand with fingers of some kind, and you grab out, and those fingers, all of the force is concentrated at those few points. Where this eddy current manipulation, it's very gentle because the forces and torques are low to begin with, but then it's also very distributed. And so you could imagine moving things that are quite fragile, I would say.
That's really interesting. Yeah, like a telescope mirror, for example, or a piece of electronics or something. You could move it into place without essentially touching it, and then be able to actually do the final connection somehow. That's really interesting. Very fascinating work.
And in a manipulation framework also, we would assume that we have a model for all of these objects, so we can model in advance how they will behave to these magnetic fields. You know, my collaborator and I are interested in the problem of coming upon an object, a piece of space debris for which we don't have a model, and can we just start manipulating it and sort of learn the model as we go. So there's sort of two parallel paths where you might tackle these in a very different way.
So what is next for your research?
We're working on so many things in parallel. We want to understand objects that don't look like solid spheres. So more thin-walled objects that might look more like many pieces of space debris. We're looking at, right now, if you look at these videos, you see that we always only actuate one of our electromagnetic sources at a time. So they each take turns, and we're choosing optimally which one to actuate at a time. And that's because we don't actually know how to actuate multiple at the same time. We don't understand how superposition works. We just know it's not linear. And
Right.
so, but we know that if we superimpose the effects correctly, we could get more than linear improvements. So like by using 2 electromagnets, we might get 4 times bigger forces, for example. So these are the types of things that we're working on now.
Oh, absolutely fascinating. It's really interesting work. I love this kind of idea, and I'm really looking forward to it being tested in space for real.
Me too.
Awesome. Well, Dr. Abbott, thank you so much for taking the time to chat with us today. If people want to follow your work, where should they go?
They can Google me, Jake Abbott. You can look at telerobotics.utah.edu. I mean, I have a Google Scholar page. I have a lab website. It's pretty easy to find me and find the stuff I work on, I'd say.
Fantastic. Well, congratulations on the work and getting in nature. And yeah, we look forward to whatever comes next.
Thanks a lot. Thanks for having me.
All right. Take care.
Good night, everyone.
All right. Let's move on to the space news portion. I guess before we go any further, I don't know how long it takes for the show to go from when we record live on Wednesday to when it goes out as a podcast, but I'm sure you've all heard at this point, James Webb has been pushed back one more day. So now it's going to be launching on Christmas, December 25th. Place your bets. Is it going to get another delay, do you think? Carolyn, you've got some James Webb things to talk about today. So why don't you let me know what you think and then go into your news.
Well, I think, sure, Christmas. Yeah. Yeah. Okay. Yeah. We can all get up at, I think it's 4:30 in the morning for you to watch that launch. It's 5:30 for me. We can all get up. I know there are several space fanatics who are planning pajama parties to watch it because we'll have to get up pretty early. But honestly, I don't know if you follow Jonathan McDowell, McDowell, but he posted the weather forecast for the next 8 days.
It's
pretty much thunderstorms. Yeah.
Yeah. Yeah.
So yeah, I'm a little skeptical. I really would love to see this thing launch. It's only been how many years, since it was supposed to launch the first time.
Yeah, I mean they're not gonna launch until it is a beautiful, clear, sunny skies, not a cloud. And of course, thanks to you, this may take a few months. Not a cloud in the sky, and then only when it's just the safest possible launch conditions will they launch it. Yeah.
Yeah, I saw a joke about it that most of the JWS people are laughing kind of weakly at. It's so powerful, it's going to look so far back in time and space that it will see its original launch date.
That's so good.
Oh, that's horrifying.
It was bad, but yeah.
So tell me about the work it's going to be doing.
All right, so it's an infrared enabled telescope. It's going to be at a Lagrange point, so it'll be well away from Earth and our heat and all of our signals. And it has a pretty complex little tent that will unfold around it to protect it from the sun and from Earth. So it should be cooling down over a period of months after it reaches Lagrange L2, and then it will start. Then they'll probably start commissioning phase and that sort of thing. And it's basically looking at anything that can give us an infrared signature. And so what fascinated me about it, I mean, it's across the board, planets, moons, stars, galaxies. But what fascinated me were a couple of aspects of it. One of them that I wrote about was about the looking back in time and space to looking at the very first stars and galaxies that would form. So we're, looking at a couple of 100 million years after the Big Bang. We'll be looking at these very first stars that we think are going to be fairly massive, kind of strange stars. They're going to have pretty short lifespans, but this is basically looking back into the epoch of reionization, when the universe moves out of the dark ages and the first stars and galaxies form. So that fascinates me immensely. I've always been very interested in that period of time. And Hubble has sort of given us a taste of that, but it's really not going to go back as far as JWST. Now, the signals that it's going to be intercepting are light that has traveled across the gap, across the universe, stretched by the expansion of the universe into the infrared. And that's what that we'll be looking at. So those first stars, those first galaxy, which are not really the full form galaxies that we see today, but are these kind of shreds of material that come together to form the galaxies that we see today. That's what it's going to be looking at.
Yeah, the way I always
distance.
describe it is that Hubble can see stuff very early on in the universe, but only if it takes a very long time to observe one tiny region, like in the Deep Field survey, or it's lucky to have a gravitational lens that allows it to use a galaxy cluster as a natural telescope to be able to see an object behind it. But James Webb will just brute force look at anything into that time regime once, which is a boon to scientists.
Yeah, I think it's going to be a monster, and I don't really know what the first observations are going to be and when we're going to start seeing this. But I would imagine over the next decade, we're going to be as amazed by what JWST turns out as we did with Hubble once Hubble's technical issues were addressed and we were able to point it and do what we need to do. I got to say, I mean, as a person who worked on a Hubble instrument, I'm just totally amazed that decades later, we're still getting science off this thing. Yeah. So I hope that the people with JWST are going to get the same thing, have that same opportunity.
Yeah. And now they're not going to be able to deliver their first images for a few months, right?
Yeah, it's going to take a while because they have to let the thing cool down. And well, first they have to get to L2 and then it has to cool down. And I forget how long they think that's going to take. It's a number of months to do that.
Months,
and then they'll start doing the commissioning imaging. Yeah. Or the commissioning observations. Yeah.
You're talking about the stuff early on in the universe, but what are some other targets, some infrared targets that James Webb will be good to reveal?
Well, another one that it's really interested me has been looking at exoplanet atmospheres. And right now we have a number of telescopes that are watching transits of planets across their stars as they orbit. If we've got the right line of sight, we can see these stars passing, between us and their stars. Well, that starlight has to filter through a planet's atmosphere. And so one of the things that they can look for is all of the chemical fingerprints of what's in those atmospheres. And some of the articles I've been reading, they're going to try and look at all kinds of planets, but of particular interest would be the ones that are Earth-like, Earth habitable. I mean, possibly habitable like Earth is in their habitable zones or somewhere near their habitable zones, and see if you'd see the chemical fingerprints of life, which I think would be oxygen and methane and things like that. So that's sort of a little bit closer to home, looking at what at whether or not there's life on those planets. And here's this telescope that'd be able to do that.
Yeah, pretty exciting. Was there anything else you wanted to cover about James Webb before we move on?
No, not really. I mean, there's a ton of science. We could go on all night with it, but those two were the things that really interested me. And I think that I'm just hoping it's going to get off on time. There is a really complex set of actions that have to happen during launch and right after launch for this thing to unfold itself, to write itself, to get it, to launch itself off to L2. And I think one of the most scary parts that I've seen people talk about is, while it's still launching, those fairings have to come off, and then we can deliver the telescope to its preliminary spot in space.
Yeah. And I think every time I talk to Pamela, she rattles off the number of actuators and the number of individual events that need to happen for this whole thing to come together. Yeah,
there's a really cool little sequence. You can go to the James Webb Space Telescope site and look at that. And it's, basically it does this, there's a firing, there's this, it does that, it unfolds this. And they're not really talking about those fairings coming off. And that's kind of what I was worried about. Once those fairings are off, then I'm going to just heave a deeper sigh of relief, I think.
And they even have plans for if it only partially works, if the sunshade only partially unfolds, et cetera, et cetera. Like, they've thought through every piece. They've had a lot of time to think through what could still happen. Yeah, absolutely fascinating. This time next week, I hope we will be looking back on James Webb launching safely, and
me too,
and looking forward to the science.
Yeah, and there's no way we can go and fix it, so we can't do what we did with Hubble.
Yeah.
Maybe someday.
It's not like Hubble. Yeah.
Maybe someday. Oh, oh, good luck, James Webb. All right,
Yeah.
Pam, what's up in space?
All right. So as you know, I like to talk about things you can actually do. Got a comet and 2 meteor showers. Those are kind of the biggies. But I do have some other highlights for the week. And of course, the Wednesday Weekly Space Hangout is a wonderful opportunity for people to learn a lot of things. We have a show on Fridays. There's the Comet Leonard, like I was saying. The 2 meteor showers are Ursids and Quadrantids. Hopefully I said that right. There's 2 contests, 1 Globe at Night project coming up, 12 conjunctions, 6 of which I think are kind of noteworthy. So I thought I would tell you about those.
Sure.
But here we have, whoops. Can we go back to the screen with the Ursids? Yeah, there we go. So it doesn't really give a range, but they do have sort of the peak, and that's basically tonight into tomorrow morning. These are coming from Ursa Minor. They appear to radiate when we get pictures of them, 5 to 10 per hour. And Comet HP/Tuttle is the source of these objects. The 2 contests we can talk about. Next slide for that is the Lunabotics Junior Contest. And I don't have a deadline for that, but I do know that they're going to announce the winners from each category next March. That's March 29th of 2022. And NASA's seeking young engineers to help design new robot concept for an excavation mission on the moon. So that's pretty exciting. I think it's really for K through 12 kids at this point, and U.S. public, private schools, homeschoolers, anything like that. Unfortunately, it is constrained to the United States. And then we have a new thing. We just found this. It's nominates a student with perseverance. They've actually got 4 rounds of this. The first one is closing by the end of December 31st. They're asking for 6th through 8th graders in, again, U.S. public, private, and home schools, but they will have a few more rounds, and they want to recognize young people for, things that they have done, and to congratulate them and offers them some nice things. The next slide has the next rounds, the dates. Yeah, they'll show each of the little things at the bottom there. We'll bring up the new dates for the next 3 rounds.
Oh, wow.
And then, it sounds really great for young people. The Globe at Night project is on December 25th through January 3rd. The southern constellation is focused on Canis Major. The northern one is Orion. Of course, that's coming up in the east now. It's a wonderful sight. And this is where you take a picture of the target constellation, you compare it to the charts they have, and report. And they have their 2022 dates up already. So that's pretty cool. On December 26th is the last quarter moon. December the 27th. This is a conjunction I think is worthy of looking for. Mercury and Venus are in conjunction.
Awesome.
Yeah.
Is your name on Mars in some way, shape, or
Yes!
form with one of the spacecraft?
Maybe a couple of them. At
Yeah.
least one. I know for sure.
Yep. Yeah, I think I'm on Mars with Perseverance.
Very cool. Yeah, I'm definitely on Mars for Perseverance. January 21st, we're into 2022 already, is the new moon. Then some more conjunctions that I think are significant. January 3rd, Mercury, the moon, Venus, and Pluto too will be all in conjunction. You'll be able to see Mercury, Venus, and the moon though, unless you have a nice telescope that you can pick up Pluto. And that's a great way to find those things because
that's one of the
near.
advantages of conjunctions is now that's a time when you know that this other object is nearby and you can find it within reference to the other ones.
Are you able to see Venus from your location, Fraser?
Yep.
Then you should be able to pick up Mercury on the 3rd.
I can see Venus, but maybe it's going to be a lot lower.
19 degrees. Well, okay, so let me get to that part.
Oh, you really want me to be able to see Mercury? But it's just not going to happen, Pam.
I'm just sad
I've
for
even
you.
got I've now got even worse horizon to the southwest than I did before.
I'm sorry.
So, it's not going to happen.
The 7th is the greatest eastern elongation. It'll be 19 degrees above the western horizon. It works weird that way.
Yeah.
So let me talk about the Quadrantid meteor shower peak real quick. That's January 3rd and 4th. It's ranging from the 27th, like a couple of days, to January 10th, and they appear to be from Draco. That's a pretty good one at 25.
Yeah, it's a good shower.
Yeah, 25 to 100 an hour. Of course, January 3rd can be pretty cold for some places. So I think that's maybe why we don't hear about it in the news more. And that comet is 2003 EH1.
Yeah.
Too bad Beth isn't here. She knows all about this stuff, doesn't she?
But the folks in the southern hemisphere, like, we've got to remember that we live on a sphere, and
Yes.
for them, it's nice in the middle of the warm times.
Yep.
So
Exactly.
perfect.
Exactly.
And Perseids are bad for them. Well, we
Yeah.
love Perseids.
Maybe it's in their news. So
Yeah.
another kind of significant conjunction is on January 4th, Saturn and the moon. And also Earth is at perihelion. And since we're not perfectly round and we're not perfectly, distanced from the sun, this is going to be the closest we get to the sun on January 4th. And of course, aphelion is when we're at the farthest point. So it's about 6 months away. On January 5th, Jupiter and the moon are in conjunction. The 7th, Mercury, like I said, Mercury is at greatest eastern elongation. January 9th is first quarter moon. January 17th is a full wolf moon. And that gets really quiet for kind of the rest of January till the very end. And there's some really cool things with that. But I'll be back by then probably.
Yeah,
So.
yeah, you save it. No spoilers.
No
Awesome.
spoilers.
All right. Thanks, Pam.
Yep.
All right, Nick, which story are you more excited about?
Kind of both. Why don't we see if we can do them quick?
Then you need to talk about them both simultaneously. No, pick. Then I'm going to choose for you. I want to talk about Pluto's cool geology.
Okay. Yeah. Pluto's really weird. It's been making some headlines recently because there's a publication that's coming out that was preambled a bit at AGU that was talking about the heart-shaped feature. This is Sputnik Planitia. So it's actually a different picture than the one that's currently showing right now. That's the first one of the Pluto pictures in my slides. So this is the so-called heart on Pluto, and it looks like a big ice field that's primarily made out of nitrogen ice. A few other things mixed in there, but it's got these big polygonal features on them. And the question was, well, how did these come about? One of the first theories that was come up with was, well, maybe it's a convective cell. So what that would mean is that there's something hot underneath, presumably, that would be making material rise, come up towards the surface, cool, and then chill down and come back down on the sides. And that makes this kind of polygonal feature if you see it in just any sort of normal setting. Here's the catch. Pluto's really small, and it's really far away from the sun. So its original accretionary heating is gone.
Right.
It also doesn't have all that much in the way of rocks and metals. So there's not a lot of radioisotope heating. So the question is, what's the heat source that would be driving convection on this? Because there's hot going on Pluto.
Right.
Well, some researchers came up with an alternative. What if instead of something hot underneath, we actually had something cold up on top? And so they started looking at the physics of sublimation. This is when a solid converts directly into a gas. It takes energy to do that. And so at a specific part of its orbit, when Pluto is as close as it gets to the sun, there's enough heat that you can actually start sublimating some of the nitrogen ice. And that starts causing the circulation to happen because it's cooling off the top relative to the bottom. It's like perspiration. When you sweat, you start to feel cooler.
Well, it's interesting.
Same
Like,
kind of
like
idea.
if you've ever used a propane tank, like here now I'm using a propane tank, and the propane tank is covered in ice.
Yep.
Because it is, I guess the gas is going out of it. It's going. Yeah, I'm not sure the exact physics that are going on. It's reducing the pressure, which is causing it to, I guess, get a little cooler. And
this is actually a wonderful high school chemistry lesson. PV equals nRT, or pervnr, if you prefer to pronounce your equations.
Right.
When you change the pressure, well, your volume's staying the same. The amount of stuff that's in there is changing, so the temperature has to change as well.
Right.
So,
yeah, and
by
so
expanding that gas out,
and so it's a similar, I guess it's a similar situation that you've got the process of sublimation going on the surface of Pluto, which is a loss of energy, which is causing this really interesting geological features.
Yes, because now the top is colder than the bottom, so the top is sinking. On the Earth, we're used thinking about things being hot underneath, so it's making the bottom rise.
Hmm.
Same process, just backward.
That's really interesting.
Now, this feeds into some of the other really weird geology that we see on Pluto, like that slide that we had up earlier. That one's looking at, I'm going to mispronounce this, pentatentes. I think I added a syllable in there. These are really big spears of ice that are actually sitting out, and they're aligned with the sun during the small portion of Pluto's year where they form. And the thought process has been for a number of years now that these can grow by 5 centimeters per year per Pluto year. And these things are a half a kilometer to a kilometer in height. So these have literally been growing for on the order of 1 billion years. It's
So
like
are those
the worst
little
kind of freezer burn.
Are those like little ripples, little bumpies that we're seeing in the picture? Are those penitentes?
Those are pentatentes.
Wow.
So these are slabs of ice that are sticking off of Pluto's surface. And what's going on is there's some interesting physics here. And you know me, I'm not the physics guy, but this is cool enough that it got me interested. You've got the point of this is really thin, so it radiates heat really well. So what sunlight hits it, it radiates back off quite easily. As it gets deeper down, that sunlight gets channelized by being reflected by the different bits of ice. And so it all concentrates in the bottom. And so the bottom heats up and you get more sublimation there, which moves more material and slowly grows those tips a little bit longer while sinking the bottom a little deeper.
Wow. That's
like
amazing.
the caves, they build their stalactites and stalagmites.
Yeah.
Different process, but
totally different process, but same kind of idea. It's these tiny, tiny changes over really long chunks of time.
Yeah.
Yeah, what is it? 249 years for of our years for Pluto to go around the sun?
Yeah.
It's
248.
some horrendously long period. I always forget.
It hasn't even made one orbit since we discovered it. So yeah.
Yep.
And I sort of think about all of these interesting things that happen. Like I'm sure you've all experienced this, where you get the right conditions, it freezes at night, and you get like the dirt is raised up on little pillars, and it sort of makes this crunch as you walk around on top of it, just because I'm not entirely sure of the exact physics that are going on, but or when an ice
one of
cube.
the other really fun ones that I first saw up here in Canada is if you get an ice patch that's really been around for a long while, it'll actually start to go through a process called Oswald ripening, which is where you go from these little tiny minuscule ice crystals to larger and larger ones, and it'll make what kind of looks like a clump of salt in the ice, where you've got these columns of ice.
I've never
and you
seen
get these ice needles the whole way through. They're not sharp or anything, but it's a really neat form.
Yeah. Yeah, and you wonder, just like with all of the forces and all of the temperatures and all of the chemistry that's going on all of these worlds, it's fascinating what nature can come up with. But I guess for you, like, this is gas doing things that are what rocks would do here on Earth.
Well, that's one of the things that's so much fun about Pluto. I mean, before we visited, before we had close-up pictures, there's a lot of speculation of saying, well, it's going to be boring. It's a dirty ice ball sitting in the outer solar system. There's not enough heat to do any kind of geology. There's no interesting chemistry. Like, why would we go there?
Yeah.
And then we see it, and our minds are blown with, wait a second, nitrogen is doing this? Oh, that's weird.
On that one. A big nope on that one, right?
Yeah,
nitrogen
glaciers.
I love it.
Yeah, all that kind of stuff. Yeah, absolutely fascinating. Wonderful. Thanks.
Well,
all right, Carolyn, let's talk about Venus.
Yeah. So recently, a paper came out from a group of people at MIT and several universities in the United Kingdom trying to figure out why they're seeing an excess or in areas of ammonia in the Venus atmosphere, in the clouds. Now, we know that the Venus atmosphere is carbon dioxide and the clouds are sulfuric acid. But why is this happening? And so they looked at a number of different mechanisms for it. You know, the volcanism isn't really causing it. It's not lightning in the atmosphere or anything like that. So they started to ask the question, could it be life that is somehow transforming from basically transforming the clouds to make its own habitable zone? And so the ammonia is can be produced by life. There are other processes. And so the one thing I do want to urge is that people don't jump to the conclusion, oh, they found life, because we've been through that, down that story before, down that story road. But what's happening is if there is life there, it's possible that they're transforming, creating the ammonia by basically living there and forming oxygen, which then dissolves into the sulfuric acid droplets and makes them a little bit less acidic. But there is this ammonia that is created during the process. They're trying to figure out why. The ammonia is not a new discovery. It was found in the 1970s. And really what they want to do is get some more data about this. So the Venus Life Finder missions could be able to do some fairly high level spectroscopy on this, on the atmosphere, to try and find more of this ammonia and maybe find a mechanism for it. But life is certainly one of the things that they're discussing.
Yeah, I saw a paper today, and I don't know if it's the same paper that maybe this was a press release that was written about, saying that actually these pockets of ammonia make the planet more habitable.
Well, that's what they're thinking. This is a group of people not headed by Sarah Seeger, but she's basically involved with it. And so she was quoted as saying this could be a place where life is making its own habitable zone as it goes along.
Mm-hmm. Yeah. We gotta get back.
And so I was thinking, and I was thinking, if it's doing that, is there some mechanism that could be useful in the future if we start seeing a lot more acidic rain here on this planet, that we could mitigate that? That's kind of far off. It just stuck in the back of my head as I was reading the paper.
So what are the plans to try to investigate Venus's atmosphere more deeply?
Well, they would be sending up the Venus Life Finder missions if everything goes well. Those would have instruments that would, I honestly don't know if they'd be sampling the atmosphere, if they'd just be doing spectral analysis of it, but at least trying to get the fingerprints of what's in that atmosphere and figuring out what are some of the other possibilities that do make ammonia naturally that maybe aren't connected to life. You have to rule out all the possibilities before you say, oh, it's life. And then you've got to figure out what kind of life is this. Mm-hmm. I don't know how much of that information Venus Life Finder, they're not built yet.
Yeah.
When they go, then we'll know what the instrument packs are, to be able to do that.
But this mission is different from other missions because it's going to be privately funded through the Breakthrough Foundation, right?
Yeah. So, but I just don't know what the final instrument selections are going to be on that.
Yeah. But in
any case, it's time to go back and look. Yeah.
Right. And I mean, fortunately, we've got two. We've got Da Vinci Plus and what's the other one? Oh, I forget the name of the other Venus mission that's planned. Mm-hmm. But I'm sure someone's going to post it in the comments. But yeah, I mean, I always joke about the fact that Venus sucks and we should push it into the sun. But it would be nice to learn a little bit about it before we dispose of it.
And what a great surprise to find if we found something interesting there, whether it's life or not. That'd be like huge.
Totally. Yeah.
Wow.
And there's so much going on at Venus anyway that you kind of have to hope, if this is really true. I can't tell you how many science fiction stories I've read over the last decades about life floating around in the upper parts of the atmosphere, or people going there to explore, and the only place they can really put a station is maybe 20 kilometers down in the atmosphere, where it's basically reasonably warm and you can float this balloon or something and live on it. There's all kinds of great ideas. So the science fiction writers are kind of a little bit ahead of us on this, but to now actually get down and dirty and build the instruments and do the science and send the spacecraft, that's really what we have to do. And that's the conclusion of this paper is need more data. We can't really say it's life, and they're very careful to say it. That we're not saying it's life because everybody remembers the phosphine discussion earlier, from that. But to say, look, there is this process. We know that ammonia is made by life. We need to rule out everything else at Venus that could be making it before we can say, oh, it's life. And then we have to find that life.
But I think that Venus is a fascinating study as an analogy of an exoplanet, showing how difficult it is to study a planet that is right next door. And when you consider like how difficult it is for us to even just come to any conclusions about life on Venus or the atmosphere, composition of Venus, etc., it shows that even when James Webb comes online, or when the Extremely Large Telescope,
Mhm.
or when Ariel comes online, when all these next generation planet hunters are operational, we're not going to have the kinds of conclusive results that we're all hoping for. We're going to have hints and possibilities, and then other teams are going to go, yeah, but here's a natural way that you could get this material in the
Mhm.
atmosphere. It's going to take a long time. I would be surprised now. I made this prediction Monday on my open space that we may not find out slam dunk that's a habitable exoplanet in my lifetime. That it's just going to be so
Yeah.
inconclusive for so long. It's a fascinating challenge. So it's great to see. I think that the people who are making all these proposals about Venus are getting a bit of a bad rap. And I think that this work is critical for us, even just being able to understand and unravel the possible biosignatures that could exist in an exoplanet. And this work is really important.
Well, think about it this way.
Absolutely.
Venus is a great place to practice on.
Yeah.
And even though we're getting a lot of indirect evidence right now, it's going to help form the scientific investigations of the next decade to say, okay, let's do this investigation to either rule in or rule out these explanations.
And it's
so it's a good place. It's a good practice target.
Yeah. When you look at the hunt for methane in the atmosphere of Mars, like that's been tricky too. Yeah. And still inconclusive. And we've got we've got spacecraft we've got rovers on the ground and spacecraft in the air, and we've got or in the atmosphere above, and an airplane or a helicopter. Like we've got everything in place to make that, and a spacecraft specifically designed to hunt for methane that's orbiting Mars, and yet it's still inconclusive. And so it just shows
very elusive.
Yeah, when you point James Webb at an exoplanet and go, we have detected methane in the atmosphere of that exoplanet. Old news. We saw it on Mars and we still don't know what it is. So anyway, I find this fascinating. I'm really excited by the work that's being done on Venus and Mars, and it's very interesting to me. Thanks, Carolyn. All right, we got a little time.
Oh, and Nick has posted the other one's called Veritas.
Veritas, yeah, Da Vinci Plus and Veritas, yeah. All right, Nick, you got one last story. Hit us.
Yes, I get to talk about rocks. So
for the first time.
I know I never talk rocks.
No.
Except, every time.
Yeah.
So the Japanese Space Agency sent a mission out to the Ryugu asteroid to collect a sample. It's Hayabusa 2. This is their second attempt at an asteroid sample return mission, and much more successful than the first one. For reference, they got about 0.2 ounces. Whoa, my screen just went funky.
I see it.
Okay, they got about 0.2 ounces of material back. That's about 5.5 grams. And they're starting to look at this and say, okay, one of the important science questions is how to relate spectroscopy of asteroids to what those asteroids are actually made out of. And then moving from there to say, okay, when we look at these materials in detail, what do we learn about the early solar system? So this is some of the darkest material we've ever seen. It has about a 2% light return, which means 98% of the visible and infrared light that we hit it with gets absorbed. That's really dark. It's also incredibly loose material. For reference, the most primitive meteorite that we've ever seen land on the ground was the Tagish Lake meteorite. It landed in Tagish Lake in British Columbia.
Mm-hmm.
Actually, not that far from you, Fraser.
Yeah, I remember. I remember when it hit, and people were out combing the ice to find the meteorite before it melted, and it was lost.
It was incredibly fortunate that it landed in the middle of winter, and a large amount of it landed on this lake that didn't have a ton of snow cap. It was just an ice sheet. And some of the people that went out hunting really knew what they were doing and collected pristine samples. But the stuff that we got from Ryugu are even more primitive than that. These are showing evidence of hydration. There's some clays. There's a high carbon content in these, which is consistent with being like a carbonaceous chondrite, a particular type of meteorites that we thought the asteroid was related to. And so this is some really exciting research starting to come out about this isn't stuff as coherent as what makes it through the atmosphere to get to the ground. So what more can we learn about the formation of planets by looking at this really, really primitive stuff? And ultimately, the formation of the planets leads into questions about how did life come about? because this would be one of the main sources for the building blocks you would need for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, all the rest of that. And so it's just exciting to see them really start to delve into this. They've done the initial characterizations, which is purely non-destructive work, trying to look at and say, what can we see before we do things where we can't get back the pristine stuff afterwards. But now they're starting to move into more destructive analyses where we'll get a lot more details about, what is this? What is this made out of, and what does that tell us about the earliest solar system?
Any water anywhere with that, Nick? And like bound up?
Yes.
Here? Oh, cool. Okay, good.
Nice. I don't know many details about the water yet because it's all spectroscopy related, and you'd have to do a destructive heating of the sample to really see how much water is there. But there's a significant OH absorption, which says there's water in there. I don't, again, know if it's structurally bound, if it's OH, if it's actual water, but they were really careful in preserving these things, either with dry nitrogen or with preserving the vacuum. So they're looking for it.
Yeah.
That's
I mean,
exciting.
it's great they have so much material to work with this time around compared to Hayabusa 1.
What was it, 2 grams for the last one, or 0.2 or something? It was really low.
It was micrograms.
Yeah.
Yeah, it was micrograms. Basically, what happened is they had an open casing that they tried to inject down in the surface to remove a plug, but instead the spacecraft bounced back, and so it just kind of scraped the surface a little bit. We got whatever dust stuck. So not a lot. Yeah. And yet I saw presentations where people were doing full-on igneous petrology of the dust grains that we scraped off of this. So it's amazing what you can get out of this.
How did they overcome that with this spacecraft to not to bounce and gather dust only? Did they
used a different sampling technique. Yeah. I'm not as familiar with how Hayabusa 2 did its sampling. Okay. I know when we did OSIRIS-REx, we actually had a gas canister stirred up the surface and essentially another canister with a one-way flap. So the gas would stir up material, knock it through the flap, but then if it had to come back out, it pushed up against the flap and stayed.
Got it.
So instead of impacting, it's just basically blowing.
Yeah.
Thank
you.
So
cool. All right. Well, we've reached the end of our hour. So it's time to move on to the shameless self-promotion portion. Carolyn, what are you working on and where can people find out more?
Well, you can read my blog at thespacewriter.com, and right now I'm working on collimating and focusing a telescope.
Yeah, I'm stoked. That's an exciting telescope that you got your hands on.
Yeah.
And there's a lot of really great science work that they're doing as well through the SETI Institute, and so you can actually like observe comets and participate in various crowd sourced science projects. So let us know how it goes.
Yeah.
Awesome.
Cool.
Pam?
Yeah, thanks so much. We are really focused in on our Friday night show. That's Everyday Spacer YouTube channel and the Everyday Spacer Facebook pages. In fact, Friday, we're going to have a happy holidays open mic night if anyone wants to join us, and we'll wish you well and then invite you to share live with us on the 31st. We're going to kind of review and talk about the cool Everyday Spacer actionables from the year. A lot of really great things happen. A lot of regular folks launched up, orbited the Earth or less. And on the 21st, we have scheduled Josh Carlson. He's coming back, and he is the author of Space Power Ascended. He'll be talking about the second space race that's currently going on with U.S. versus the China-Russia team. And you know what? We invite anyone who would like to come and talk to us about space exploration, science, and astronomy. Anybody here, anybody in the audience, we would love to share our live with you.
Fantastic.
Thanks.
Nick?
I'm still working on my course, so I'm getting ready. I'm getting pretty excited about it. My course, by the way, is called How to Live on Mars and Not Die. If you are interested in listening to, well, me talk about what it could look like if we sent humans to Mars, or you know someone who might be interested, makes a great last-minute Christmas present. Anyway,
awesome.
You can find it on Eventbrite. Just look for How to Live on Mars and Not Die.
And if people want to find out what you're working on, what's the best way to follow you?
Well, you can follow my largely inactive Twitter account, which I need to get better at.
No, don't
Uh,
never feel any Twitter guilt.
oh, I
Never.
have copious Twitter guilt.
No, just
I'm
the fact that
wandering
you
side.
literally have a Twitter feed, that's enough.
Ah, excellent.
Yeah,
Well, in that
make
case, minimum
courses,
success criteria achieved.
study Mars, much better use of your time than being on Twitter.
Details. My Twitter account, I actually have two of them. One where I post about my exploration of the national parks called Wandering Sci. That's Wandering SCI. And one where I am talking about all things planetary science. That's Planetary Geodoc. So you
Fantastic.
can follow either of those or both.
Excellent. All right. And I'm not going to do anything. So you can, of course, follow everything on Universe Today. I will be back here next week because we never take a break. But Astronomy Cast off for until the new year. I'm not doing open space until the new year. So I will be writing a newsletter. Maybe not on Friday. That might be a little tricky. Maybe I'll take 1 week off. But apart from that, we'll have lots of cool space news coming up on Universe Today. So thank you, everybody, for joining us this week. Thanks to our special guests. Thanks to all the co-hosts for hanging out for the hour. Thanks to everyone watching on both YouTube and on Twitch. All of the moderators. Special thanks to Nancy Graziano for keeping us all organized and Pamela for engineering behind the scenes. Thank you, everyone.
Yeah.
We will see you. I hope you all have a safe holiday, and we will see all of you next week. So no breaks for the Weekly Space Hangout. All right. Thanks, everyone. See you next week.
Bye.
Bye-bye.